Okay, so for the second of the lecture series, we have Mitchell Luskin from the University of Minnesota, and he's going to be talking about mathematical modeling and numerical analysis for incommensurate 2D materials. Go ahead.
Okay, thank you, the organizers, for inviting me here, and the Newton Institute, and having a great visit. So what I'd like to do, well, the first lecture is going to be introductory, mainly about single layer 2D materials, which is not really the topic of my kind of lecture series, but you have to know about single layers to talk about bilayers, of course. And so I'm going to give you, so everything I say is about the physics is the physics from the perspective of a mathematician. Okay, so so you may get a different picture from talking to a real physicist, but this is my view of the subject. Okay, so the work I've been doing has had many collaborators. So there's a long list there. I'm not going to specifically talk about who did what on the various kind of contributions, but I'd like to acknowledge all of them. Okay, so I think pretty much everybody, I'm sure, has heard about 2D materials, and it was actually the kind of most of the mathematics I'm going to talk about, physics, in this first lecture was actually done in 1947 by somebody named Wallace, and he was just studying things like band structure of 2D hexagonal structures. I don't know why he did this. Maybe he was just trying to find some textbook kind of way to understand band structure, but he found some very interesting things, which I will review. Okay, so the modern subject was, well, there were actually many people contributing to this and trying this, but the big breakthrough was when Gaiman Novoselov and his group, which are in Manchester, which is of course sort of a local product, exfoliated a single layer of a hexagonal carbon structure from graphite. Okay, so let me just show you here. This is me in the lab, and so and again, you probably have heard about this, and so it was done by the famous Scotch tape method. So it means you take graphite, which is a bulk 2D material, and remember, graphite is a lubricant. So a lubricant means that individual layers are strongly bonded, okay, but the layers themselves slide easily, okay, and the interactions there are rather weak, van der Waals interactions, and that's why it's a lubricant, because one layer can slide on another. It also means that you can pull a few layers off with Scotch tape, okay, and so then when you pull some few layers off with Scotch tape, well, you're not done yet because you don't have a single layer, but then you sort of get another layer, and you keep kind of pulling off layers till you get down to a single layer. Okay, so actually, if you really want to see a very fun video, go type on type into Google, those, not necessarily those who are during my lecture, but just type how to make graphene Harvard, and you'll get a great video with music by sort of a grad student here in Philip Kim's lab. That's really fun and shows you how to do it. Anyway, so this is a Scotch tape, so it's real Scotch tape. Okay. So what is the structure of graphene? So as I said, it's a hexagonal structure of strongly bonded carbon atoms. Okay, and so now it has very amazing properties. So what we'll see, and I'll actually run you through the computation. It actually has what's called a linear dispersion, the famous Dirac cone. Okay, so that's so that has many consequences. Then it has obviously inversion symmetry. It has extraordinary mechanical strength. Okay, so obviously it's as a single layer material, it has amazing strength because of the carbon bonds. So if you scale the normal parameters of elasticity, I'll talk about elastic properties too, it has enormous strength. So it has interesting electronic and mechanical properties. And so there are all kinds of amazing physics that have been and are still being done on graphene. And I'll just talk about a little of it. Okay, now the problem with graphene is it's what's called a semi-metal. Okay, and I'll explain what that is. It means there's no band gap. Okay, and so people are looking for 2D materials that have, that say maybe they're insulators, maybe they're semiconductors. So now there are, I don't know what are, 7 or 8 2D materials that have been exfoliated. And probably the one that's very useful is hexagonal boron nitride. It's an insulator, it has a band gap. And so that looks just like graphene, except now we're alternating 2 atoms. Okay, and it's often used to encapsulate graphene. Okay, now a few others in the kind of, let's say, table of 2D materials that are very interesting. So here's molybdenum disulfide here, and so this is a little more complicated structure. It's not just a single layer in the plane. Okay, it's a single layer, but it has a little more complicated structure. But it still is hexagonal, and it does have a band gap, so it is a semiconductor. So these are very interesting class of 2D materials. Now, one that was kind of a rage, still is of great interest, but last few years is what's called black phosphorus. Now, this is a anisotropic material, but also a little more complicated structure. Okay, now why do I care about all these different 2D materials with their different properties? Well, the goal of this is a true materials design problem with a high dimensional parameter space. So think of this. You can take I just showed you 4 different 2D materials. People now have control to put one on another and to arbitrarily rotate one on the other. So when you rotate, let's say, one layer of graphene on another, you change the properties dramatically. Okay, so now you have a very high dimensional space. So this is actually this was probably the first paper I read on the subject, and so Geim views this as sort of as Legos, but they're actually not Legos. Legos implies they stack nicely together, and that's the problem is that they don't stack nicely together, right? They have the lattice spacing is incommensurate. Okay, so the idea is to again stack these in various orders at various rotations and try to design electronic optical devices with custom properties. Okay, so this program, by the way, is really going full blast. Okay, so what makes it interesting is we'll see we have to deal with incommensurate lattices. That means you put one lattice on another, and the combined system's no longer periodic. And we want to predict electronic and optical properties. Okay, and this just shows you some other little devices you can make. Okay, so let me get down to talking about the mathematical structure. So, okay, and please ask questions if you have any during, as I go along. Okay, so, okay, what is a Bravais lattice? I mean, I'm guessing most of you know about this, but simply, it's just some linear independent set of vectors, and we look at their span, and we can just describe it this way as taking a invertible matrix and apply that to Z2. This is a Bravais lattice, and it has a unit cell associated with it. It's just all the points in, say, in the smallest cell generated by that lattice. Okay. Okay. Now we associate to every lattice point a set of m orbitals. Okay. Now what do I? Now those orbitals can be. Let's kind of go back here to graphene. So graphene, right, is not a Bravais lattice. Okay, but it's a lattice. If you just look at, say, this, if you take every, if you this is your lattice vector, and you just say, and this is another lattice vector, that's a lattice vector, and you say you have an orbital here and an orbital there. Okay, so the other orbitals, the orbitals in the script A can be centered at what's called the basis of the lattice. It need not be centered at the actual lattice. So that enables us to, again, accommodate complex 2D structures. So even something like this is a lattice, right, with a basis, with a set of orbitals that are centered. Some are centered at the lattice point. Some are centered other places in the unit cell. Okay. Okay. So. Okay. So here, this is our. You might call this the total. Okay, omega, which is the cross product of the lattice and the set of orbitals, that's our total degrees of freedom. Those are our degrees of freedom. Okay? Okay. Now, another thing that's quite useful is what's called the reciprocal lattice. Okay, so reciprocal lattice just means, I should have written this down, it's just here, that it's just described by A minus transpose. Right, it just means that the reciprocal lattice vectors are orthogonal to the, mutually orthogonal to the lattice vectors. Now the lattice vectors need not be orthogonal, but the reciprocal lattice vectors are orthogonal to the lattice vectors. So the reciprocal lattice is very important, and its unit cell is what's called the Brion zone, and that's super important because this is the Fourier transform, right, will actually live in the Brion zone, the band structure. We'll see that. Okay, so here's a messy slide. Give you a little more feeling of the structure of, and I'm just doing this for graphene because it's the simplest structure. You could do that for any of these other 2D materials. Okay, so here's our hexagonal structure. Now the blue and the red atoms, they're both carbon in this case. Okay, they're both carbon in the case of graphene, but we call the blue atoms A and the red atoms B atoms. Okay, so A1 and A2, those are our lattice vectors, right? These are the vectors whose integer multiples span the lattice, right? And here's the corresponding matrix. Okay. Now, and then, okay, and here's a unit cell. It's not centered at. Okay, it's centered in different. Okay. Then the deltas are pointing to the nearest neighbors, right? So the nearest neighbor points you not to another lattice vector, because the hexagonal structure is not a lattice. Okay, so these are the pointing to the nearest neighbors. Okay. Then, now, what is the reciprocal lattice of A1 and A2? That's B1 and B2. Okay, so this is the reciprocal lattice. So remember, so B1, right, will be orthogonal to A2, and B2 orthogonal to A1, and then now okay, here we visualize the Brion zone, right, the periodic structure as being centered at this point gamma, and so it's going to be we have a hexagonal kind of structure, but again, it could be, this is just any lattice has a repeating structure, right? The unit cell can be kind of centered wherever you want. So it's just this way of visualizing the unit cell in reciprocal space, the Brion zone, kind of exploits all the symmetry of the crystal. Okay, So here's lattice vectors, reciprocal lattice vectors, nearest neighbor vectors. Okay, now the nearest neighbor vectors for B, and this will be important, are actually minus the nearest neighbor vectors for A. Okay, now what's very important are what are called the Dirac points. So the Dirac points are these points in the unit cell of the reciprocal lattice. Okay, and these are the points where the Dirac cone is centered. Okay, so they play an important role. Oops, down. Okay, so most of what I say here is going to be based on what's called a tight binding approach. Okay, so so everybody knows about Schrodinger's equation. It's a PDE. Okay, so Schrodinger's is a PDE. But if you really want to solve the Schrodinger equation, say density functional theory or anything like that, you can't solve a very large problem, right? You can only solve for, So, we're going to want to solve large problems involving large numbers of atoms. And so we can't solve a very complicated PDE. We have to solve a very simple actually matrix equation. And that matrix equation is nothing other than, say, a finite element, or it's nothing other than a Galerkin approximation of the Schrodinger equation with a very special bases. And those bases are centered at the atoms. They're called orbitals, right? As you might imagine. So we're going to deal with a Hamiltonian. So the real Hamiltonian, right, is this PDE. Okay, but we're simply going to project that PDE onto this set of basis elements, orbitals. Okay, now we index those. How do we? Now this key. Remember, since we have a repeating structure, those orbitals, right? We just compute we compute the orbital at one lattice point, and then that serves as the orbital for all the other lattice points just by translation. Because remember, we have all that symmetry. Okay, so you just compute phi sub alpha. Like that's just an orbital at say that the origin of your lattice, right? And alpha indexes whether it's the A atom or B atom. Okay, then. So so in the case of graphene, the simplest case, when you just have a pz orbital, that's the most important orbital. When you just have, and we just have two functions, right? We have two functions for alpha 1 and alpha 2, or alpha blue or alpha red. Okay, and then from this we generate these orbitals centered at all the other atoms. All the atoms have a function associated with them, and so this is our sort of approximation space if you've studied numerical analysis. And then simply this Hamiltonian operator is just what we get by this approximation, of the Schrodinger equation with respect to these orbitals. Okay, now. The important thing here is, right, so we can characterize this operator here, right? I mean, if it was, you could view it as like sort of an infinite matrix, and these are your indices here. And the important thing to realize, right, is that we have translation invariance. This is very important, right? We have a crystal, you expect it. So the elements of the Hamiltonian have translation invariance. These are sometimes called hopping functions. Okay, and then we have a mass operator, which is normally just the identity. Okay, and then there are various elaborate ways to compute these orbitals that part of this project done by some of the people on that long list of people have actually computed these orbitals from DFT. So all the work that I'm going to present is not just made up numbers. We actually start from a PDE, Schrodinger's equation, and then we compute orbitals, okay, by the Varner orbital construction method. Okay, so everything is all the errors are pretty controlled. Okay, so here, as I said, I'm just repeating myself. So we model the we model these pi bonds of the pz orbitals at the sites from the sites A, B, right? And these are our labels. Okay, and this is the right. This is the famous Wallace model that I mentioned. Okay, so in this model here, this is just again, just a Hamiltonian, right, or just a matrix, an operator, say. But if you can think of it as a matrix, okay, and it just says that we have the diagonal elements are epsilon, and then the nearest neighbor interactions are just t, okay. So yeah, like if you're just, let's say you're just discretizing Laplace's equation with a finite difference method, right? Then you get some, t would then be what 1/h squared, and this is what minus 2/h squared, or something like that. So this is a very simple matrix, okay, or operator. Okay, so remember these R alpha is like an index of your operator or matrix. Okay, R tells you which lattice point it is, and alpha says whether that's the A or B orbital, right? And so it just says that when R alpha is equal to R prime alpha, okay, then when they're equal, it's epsilon, okay, and then when they correspond to nearest neighbors, it's t. So very simple model. You can do some of this with more complicated models, including next nearest neighbors, et cetera, et cetera. But this is the simplest, and we get a lot out of this very simple model. Okay. Now, so what is it we want to do here? We want to we want to solve for the eigenvalues and eigenvectors. Okay, that's the traditional problem in quantum mechanics. Find eigenvalues and eigenvectors of this very special operator. Okay. Now, since H is translation invariant, right? It's like a constant coefficient PDE or anything. So how do you solve constant coefficient problems? You take the Fourier transform. Okay. So the physicists call this the block transform. Okay. So let's just say we have a state, right? Defined for each alpha, right? We have a state or a function in our Hilbert space, L2 functions on the lattice, okay? And then we can just describe its discrete block transform, right, simply by taking, it's just a discrete Fourier transform, okay? Again, if you've ever analyzed constant coefficient finite difference methods, this is exactly what you do, okay? Since I'm primarily a numerical analyst, I've done this many, many times in classes. Okay, so now this Fourier transform is periodic on the reciprocal lattice. Okay, so that's okay. So and we've seen what the reciprocal lattice is, and we can recover, right? Okay, so in other words, this is a function of all Q, but in fact, it's really periodic on this unit cell in reciprocal space. Okay, so right, so if the lattice vectors got smaller and smaller, then you'd eventually converge to the classical continuous Fourier transform. This is just the discrete version of the Fourier transform. Okay, so now we have, as we normally have in Fourier analysis, we have an inverse. We can recover the function, right, from the block transform just by integrating over the unit cell, the Brion zone. Okay, so this is the tool. This is our Fourier tool. We're going to apply to this Hamiltonian problem with translation invariance. Okay. Again, if you've ever solved Laplace's equation with the Fourier transform. This is all we're doing here. Okay, so now, if I just do this calculation, right, here's the, so I apply the Hamiltonian to a state U. Let me take its block transform, Fourier transform, and lo and behold, it turns the operation of the Hamiltonian on the state U, it turns it into multiplication, right? That's what Fourier transforms do. That changes, it converts you from your PDE problem to a multiplication problem. Okay, so in matrix form, right, this is our new eigenvalue problem. Okay, so now, okay, so let's say we have m orbitals, right? We have m orbitals associated with every lattice vector. Then instead of solving for the eigenvalues and eigenvectors of this very complicated matrix, what do we get to do? We only have to solve a simple m by m eigenvalue problem, right? In the case of the graphene with the nearest neighbor interactions, we just have to solve a 2 by 2 eigenvalue problem. And these eigenvalues and eigenstates, right? This is what's called the band structure. Okay. So let's actually do it for graphene. Okay. So here's, and now I'm going to let epsilon equal 0 because that's just adding a constant to your operator, right? And that doesn't change. It just moves all the eigenvalues systematically. So let's just take this Hamiltonian that has only nearest neighbor non-zero entries, okay? And now what I want to do is I want to actually compute, right? For Q is any kind of that's just your momentum space coordinate, okay? Maybe you might want to call it the momentum, whatever. But okay, just your momentum space coordinate. And for each Q, I need to solve. I want to take the Fourier transform. So I just go to the definition, right, of the block Fourier transform, okay, for this particular problem. So H11. Remember that means that's the interaction of a site with itself. That's 0. Okay, so that's 0. H22 is 0. Now these are interesting here. This says I want to get the 1, 2 entry. And so what I do is I essentially add, this is now the matrix element, the nearest neighbor matrix element, right? And this is now, again, evaluated at the nearest neighbors. And this is the R, that R comes in. Anyway, you just calculate, so I just calculated it, okay? And then, of course, the H hat 21 is just the complex conjugate of that, okay? So in fact, this is a very simple matrix. It has 0 on the diagonal, and it has an entry and its complex conjugate on the off diagonal, okay? So that means that the eigenvalues are just plus or minus the modulus of H12, and so here it is, okay? So we've actually computed all the eigenvalues, right, of that kind of Wallace-Hamiltonian. This is all the eigenvalues of that Wallace-Hamiltonian. Okay, so now, what is that? I can plot that picture, right? I can plot it. I can plot the eigenvalues versus Q. This is our Brion zone, and this is what it looks like. Remember, so we have plus or minus. This is repeated down here, and so what do we see? We see these singularities, right, at the K and K prime points. Those are the famous, like, Dirac cones, okay? So normally you're dealing with parabolic structures. Here, you really have a linear kind of dispersion, what's called. So I can actually linearize h hat of q about either k, which or k prime, like I could combine the description where I take tau is equal to 1 for k and tau is equal to -1 for k prime. Okay, and then here's our so here's our Fourier transform, right? This is what it looks like, right? I guess. Okay, this is the linearized. I linearized that nonlinear problem around the k and k prime points. Okay, and okay, so we can write it this way, and here's the eigen values. Okay, and we can also write the eigenvectors, right? And we also can compute the eigenvectors. Okay. Okay, now, this is something that I'm not going to talk much about here, but this is like a really hot area. This gets into all this topological properties of materials and helicity, and that is that K. Okay, so I talked about band structure, and band structure. There's a topology associated with band structure. Okay, you may have heard about things like Berry phase and Berry curvature and all this. So this is so there's a topology in the band structure, and you can already start to, and so people are exploiting this in all kind of physics, but you can see it right here in this very simple model because this is our eigenvector. Remember, tau is 1 for k, and tau is -1 for k prime. Okay, so that means that if you look at this eigenvector, right, then this first coordinate, it winds -2 pi. Okay, if I go around, clockwise, then the argument around k is going in the counterclockwise, and the argument around k prime is also going clockwise. So, so there's a definite difference in the topology at k and k prime, right? So, okay, so that's very interesting, and people try to exploit that in various devices and things. Okay, there's a subject called valleytronics, where people try to look at propagation in the different valleys, meaning around, essentially creating wave packets at k and k prime. Okay, so here's our now. So you may have heard about, somehow there's this Dirac Hamiltonian around here. Like, okay, so where does that come from? That comes from, so here's my momentum space Hamiltonian, okay, and now I just go and replace the Fourier variable q by I times the derivative, right? Because when you apply I times a derivative, then in Fourier transform space, that's I times the whatever it is, the reciprocal function. Okay, so you just simply do that. You just say, okay, this is just the Fourier transform of this PDE. Okay, now this PDE, this is a Hamiltonian PDE, a 2x2 PDE. Okay, and you can write it this way. Okay, and so people often say this corresponds to what's called a massless Dirac Hamiltonian. Okay, and you can play with this. Here's your kind of time dependent equation. Okay, so so I got this very simply just from tight binding approach. Okay, there's actually very interesting mathematical work by Pfefferman and Weinstein, where they essentially look at the Schrödinger equation with a potential with hexagonal symmetry, and they look at wave packets, and they kind of they study this equation, show various properties of this. So you can actually get this. So they've actually kind of rigorously kind of studied this from the point of view of just a scalar Schrödinger equation with hexagonal potential. Okay. So, by the way, so people talk about, f sub v sub f is what's called the the Fermi velocity. So, okay, so somehow people think, okay, you know, these quasi-particles, whatever, are traveling at that speed, and okay, so that's okay. So this okay, so this is okay. So what I've reviewed here is sort of like the kind of graphene 101. It's the, you know, I've kind of done it in sort of a little bit, you know, my way as a mathematician. But these are the essential properties of that kind of Wallace Hamiltonian. Okay, now let's look at a few questions here. So one of the things that physicists really like to study is the density of states of a Hamiltonian. So the density of states is okay. So if you just you know, graph all your eigenvalues, okay, and now you just look at, you say, okay, I kind of bin all my eigenvalues, and I want to know what is the density of eigenvalues as I look through the spectrum, right? There may be more eigenvalues at 5 than at 3, etc. So what is the density of eigenvalues? So this is a very, very important in many physical models. So this is kind of like the most basic question to ask about an operator, okay? Okay, so I'm going to play a little game here, just to kind of, because, you know, it's all real simple in a periodic structure, but when we go to incommensurate, none of this is trivial. Okay, so let's, if I ask you for the density of states of an operator, okay, then the natural thing is to say, okay, let me just have some cutoff. Let me just cut off the lattice with some ball of radius r, or maybe I just take some periodicity of scale little r, okay? And now I just go look at this projected Hamiltonian, right? The far field's cut off, and now I literally have a matrix, and I can talk about, I can try to study its you know, distribution of eigenvalues. Now for a matrix, right, the eigenvalues are discrete. So now the density of states is just a sum of delta functions, right? When we go to infinite, it becomes continuous. Okay, so we can, okay, so the spectral measure, right, what is the spectral measure? I mean, it's just the density times dE. That's what I call the spectral measure. Okay, so you can compute the spectral measure just by taking the trace. You know, okay, you want to know the spectral measure, take some arbitrary test function, phi, apply that to h of r, and take the trace of that, then normalize. Okay, so this is just for any continuous function. I can compute this. Okay, and then that just means there's a unique measure associated with that, right? You know, d mu sub r. Okay, so just, you know, whenever you have a functional of continuous functions that defines a measure. Okay, so this is okay. Then that measure gives the density through this. Okay, so that's okay. So if you really want the density of states as a function, right? Then you can take phi to be a Gaussian centered at some energy. That gives you something. You know, close to that. I mean, the real thing should be a delta function, but we actually, from all our numerical processes, it's actually better to actually have to use like a Gaussian and compute that. Okay, I'll explain that as we go along. Anyway, so then you could say, let's look at this, and now let me just take r goes to infinity. Does this thing have a limit? Okay, now. In a periodic problem, it's pretty clear it has a limit, right? And I'll show you what it is. And incommensurate, it actually took us a long time to figure out that it did have a limit. Okay, so so does this have a limit? By the way, of course, yeah, you know, defining a function of a matrix, you have to use some Cauchy formula, which I'll show you as well. But okay, for polynomials, it's straightforward, of course. Okay, so how do we compute the density? Well, you can just compute the density, right, by summing over all the bands, and then just take the delta function. that just gives you, this says, okay, at a given energy, this just says how much do you pick up from that band, okay, so you get to that integral, then you do some change of coordinates and you get this. That just says, okay, I now I look at what do I do? I go, and by this, so this is the density of states for graphene. Okay, so let me go back here. So what I would do is I'd say, let me just go look at this energy here, okay, and then I would just go around this circle, and then I'd have to compute the the denominator. I'd have to normalize this by the gradient of the band energy. Anyway, this is you can calculate this. Anyway, so in this case, the density of states has an analytic formula. Okay, so remember we have and this is all real nice because it's a periodic problem. Okay, now another thing we're going to be interested in is studying conductivity. Okay, so so conductivity is the response of a charge to an applied field, right? We know that. And so we can actually use what's called the Kubo formula. It just says, okay, you apply a small field, you see, then you just calculate what the response is. And so you can derive this formula. And again, this is the formula. Okay, so this is not really what okay, so this is, how do I interpret this formula? This is kind of setting up a density matrix. This is kind of like how the system propagates with respect to the Hamiltonian, right? And then, so now we have a density, right? And then we multiply it by a current operator and take its trace. Anyway, so this object here is, it lets you go from the band structure, right? From the band structure, well, if you can compute the eigenvalues and eigenvectors of the matrix, right, then you can compute the conductivity, the linear conductivity. Okay, and these are what these operators are. This is going to be useful. Okay, so this is what's called the current operator. Okay, so given, just as you take the commutator of the position operator in H, okay, so that's what this is. This is what's called the Liouvillean operator. This is what's called the Fermi-Dirac distribution. That just gives me the distribution of states at a finite temperature. Okay, so we actually don't. Okay, so the form that we actually kind of study the conductivity is this form here. Okay, this is actually what's in. If you go to, I found it in my collaborator Tim Kixeris's book on electronic properties of solids or something. If you go back, when you go see how he treats the Kubo formula, this is the formula that you'll see. Okay, so so what do we have here? We have the we have the these velocity operators, right? And then these are the eigenvalues, eigenvectors of the Hamiltonian. Okay, and then this is what we call a conductivity function, and that's this kind of complicated guy here. Okay, so a couple things here. Let me go back to this. Okay, whoops, did I write that down? No, it's the next slide. Okay, so, oh, here it is, sorry. Okay, so this is our conductivity function. So, okay, now, and this is what's called the current correlation measure, okay, because these are, again, two current operators kind of multiplied by each other. Okay, so in fact, this is really what's used to compute the conductivity from the band structure, okay, for a periodic problem. And the question that we will address is how do we do this for an incommensurate system? Okay, and I haven't really even told you what incommensurate system is, but this is kind of like these are like the kind of properties that we're interested in. These are measurable physical quantities that we can compute, right, from a mathematical model, right, the Schrodinger equation, and then the tight binding approximation. Okay, so then you can look at, okay, you can ask again, let R go to infinity, and you compute the, a form of the conductivity that's a little more elegant. Okay, so how to generalize to incommensurate multi-layers. Okay, so I'll get to that in a minute. Let me just finish, let me just say a few words about deformation and elastic energy, because there's some interesting mechanics in incommensurate 2D materials. So, the single layer, often we just use isotropic linear elasticity for graphene. Okay, you can add in nonlinear effects, bending effects, et cetera, et cetera. But this is a pretty good model for if you don't have defects and things for the elastic energy of each layer itself. Now the problem is how do they interact? Okay, and that's the subject of the next lecture, in fact. Okay, so now let's talk about incommensurate materials. Okay, and where do they come from? Okay, so okay, this is just a little figure. That just is okay. Let's just take black phosphorus, molybdenum disulfide, put that on top. Put a graphene on top of that, put another graphene, rotate it, and put hexagonal boron nitride on top of that. And these two graphene layers are they're sitting there at some angle. Okay, one's twisted with respect to the other. Okay, now and the key thing is that the lattice spacing, right? Lattice spacing in each of these materials is different, and since they're not rationally related, right, they're incommensurate. There is no periodicity, okay, in general. Okay, now if you look at it, if you look top down on this, okay, so the way I like to explain it, for a periodic problem, right, if you stand on any atom in a periodic structure and or somebody just puts you on an atom in a periodic structure and you look around, you can't tell the environment from any other atom. It would all look the same. But in an incommensurate material, every atom has a unique environment. Okay, so if I'm looking at this structure, and I tell you, and I just plop you down over here on this phosphorus atom, and I tell you what the environment is. That means, okay, where look around, like how close is this atom and that atom at what angle? Okay, if I tell you that information, you will know that you're right here, not there. Every atom has a unique environment. Okay, so it's totally the opposite of periodicity. Well, not, okay, there's some order here, but nonetheless, it's, okay, so that's what incommensurate is. Okay, so here's another way to, okay, so let's go look at a simplest case of graphene. Okay, I take just a hexagonal structure. So let's let the blue atoms be a single layer of graphene. Okay, now let me put another layer of graphene on top of it. Okay, and I want to twist it. Okay, and okay, so let's say let's say I twist it to the to this red, to this theta 1. If I twist it by theta 1, okay, so one layer, they're not just sitting there on top of each other, or with the same kind of lattice structure. I actually put one at a twist on top of the other. Okay, now if it turns out, such as in this theta 1, if it turns out that if I can draw this arc from this atom here and I can hit another atom, what that means is for that angle I do have a periodic structure. Okay, for that angle I do have a periodic structure. But I think it's pretty clear to see that for the number of periodic structures is discrete, right? Well, okay, so so almost all, pretty much almost all angles are incommensurate. There is no, there is no periodicity with that. So again, so if you just kind of, now you might ask, okay, so Now you might ask, given some angle, if I don't pass through any, giving some angle, generally I'm not going to pass through any blue atom. If I just have a red vector, generally I'm not going to pass through any blue atom, right? If I do pass through a blue atom, that means I have a periodic structure. If I don't, it's not periodic. For a general, angle does not pass through any of the blue atoms. And you might say, for material properties, maybe I can get everything I want from something close by. That is periodic. That's called a supercell. Okay. Now it turns out that that's fine if the supercell is not too large. Okay, and I mean even there it's not totally well understood when. So what people normally do is, and when we got into the business, is that's how pretty much everything was done. You look in the literature and you say for what's supposed to be at they say some angle, okay, and then what they do is they don't really solve it, or they actually choose a special angle, and you can write down a formula for those special angles or some Diophantine equation. They choose a special angle so they have periodicity, and then once they have periodicity, there's all this software based on periodic stuff, all these band structure codes. You just have to feed it into them, and out comes your band structure. Okay, but in general, then other times people do things like let's say if you have, instead of rotation, you have one 2D structure on another, and their lattices are different. Then they'll strain one of them to make it periodic. Okay, now then they hand it off to their band structure code. But again, now their band structure is not really, it's not really, graphene molybdenum disulfide. It's something else. Well, it's not graphene molybdenum disulfide. I'm just making this up. But it's not in the ground state that you would find it. They've actually have to stretch they actually stretch both of the materials to make them have a small periodic cell, and then they do their work. So the methods I'm going to tell you about really let us directly attack aperiodic incommensurate structures. Okay, now another thing too is there's been a lot of interest in a lot of interesting physics at what's called the small angle case. Okay, so people now can control like down to 0.1 degree, I think even maybe even 0.01 degree. So they have a lot of control of the angle of one layer on another. So if you have a very small angle, then even if, and you can see it from this picture, even if it's commensurate, even if you hit a blue atom, it's going to be way out here, meaning your kind of periodic structure is going to be enormous, too big to solve a problem on. Okay, so so our methods let us solve for band structure or density of states, all these things, conductivity at arbitrarily small arbitrary angles for that matter. Okay, so here's the little computational goals. And so a lot of what I'm going to do, I'm going to talk about some formulations, and our goal is always an efficient computational method. Okay, so once you have the right model and formulation, then usually the efficient computational method follows along. Okay, so as I mentioned, the size of you can approximate the incommensurate structure by supercells, but the size increases quickly for low-angle twist. You have uncontrolled unknown error, and so the methods that I'm going to show you, they essentially they sample what's called configuration, exploit locality, and we can now efficiently compute the full parameter space even for low angle twist. Okay, and again, being numerical analyst, we like to say we have a controlled and known errors. We actually do. We have real error estimates for all the approximations. Okay, so let me just, I will stop on time, but let me just kind of start up a little bit on some of the notation for 2D bilayer geometry. So let's say we have two sheets, and then we have two Bravais lattices, right? And we can define the unit cell for each layer, each Bravais lattice, right? Each individual sheet is periodic. However, the union of the two Bravais lattices, right, need not be periodic. Okay, that we just saw that simply by, in the case of just graphene, one layer of graphene rotated on another. Okay, and then of course we add on the basis, the orbitals to each lattice, and so this kind of notation, it can be a graphene on graphene, or it can be graphene on hexagonal boron nitride, right? It can be the same material or a different material. Okay, so again, now we can again derive compute a Hamiltonian with respect to these orbitals. Okay, and then we can compute our we can describe our the matrix in terms of this operator here. Okay, these hopping functions, and we still want to look at this eigenvalue. We're interested in density of states, conductivity, et cetera, et cetera. Now, this new operator for the incommensurate system, right, it does not have translation symmetry. So I don't have that block transform anymore. So what do I do? I don't have a block transform. Okay? So this is kind of in a nutshell of our new approach. So most of the physics stuff says, okay, take an operator, take its trace, and you get to decide, right, what the basis is. What basis you write that operator in. Is it going to be real space, momentum space, right? And so so basically, then you have to integrate over that Brion zone. Okay, so remember my slide on the block transform and its inverse. So our new basis is this local configuration, okay? So here you see, one layer twisted on another, okay? And that's it. Now you may notice some global pattern. Those are called Moiré cells, very important. Okay, in fact, a lot of people call this Moiré physics and this and that. So you do have when you have two, this is well known in art and even, or anything. You take one. You take some periodic structure and you put one on top of it, some slight angle or twist, then you get a larger periodicity. Okay, so that's, I'll talk more about that. But okay, so let's look at three different, as I look through this lattice, right, I look at three different red atoms, and I look at its environment, okay? And so we see the three different red atoms, and we can describe that environment, right, by a vector from the red atom to this kind of nearest blue atom, right? Okay. So each of these atoms, each of these red atoms has an associated. It's actually a shift. It's a dysregistry. Okay, that totally characterizes the environment, okay? Now, it turns out there's actually a one-to-one mapping, okay, between the environment of all those red atoms, okay, and the unit cell of the atom of the layer above you, okay? So in other words, as I move through this structure, these vectors are going to be uniformly distributed in this unit cell, okay? It's going to be uniformly distributed here in the unit cell of the other layer, okay? And we can go back and forth. If I choose a point in the unit cell, I can tell you where I am anywhere in this material. So what that means is I can actually describe an infinite system, right? An infinite system. I can give it a rather compact. I can actually describe it in a compact continuous set. Okay. In this case, if this is gamma 2. If the red is the lattice 1, R1, then this corresponds to gamma 2, the unit cell of the other lattice. Okay. So the local environments, and simply I can, instead of integrating over the Brion zone, okay, the Fourier variable, I can integrate over configuration space, okay? So this is, so we're going to use this approach for mechanics, electronic structure, transport, even the interpretation of diffraction. What is diffraction, right? Diffraction says take a Fourier transform of a periodic structure, okay? So how do we interpret diffraction off an incommensurate structure? The same ideas will help us do that, okay? So let me just kind of close here with, this is probably a good place to close, but it's just that ergodicity result I just mentioned. Okay, so thank you very much, and we think 9 a.m. tomorrow morning.
So we have time for maybe one quick question. Otherwise, Mitch would be probably available at the reception that just follows this. Any quick questions? Okay, so let's thank Mitch again.